In this video tutorial, we're gonna learn how to solve first-order homogeneous ordinary differential equations. Homogeneous ordinary differential equations is of the form m of xy dx plus n of xy dy equal to 0. Given the equation dy over dx equal to x plus y over x minus y, solve for the solution. By examining the equation, we notice that it is impossible to separate the variables. So what we do first is bring this up right here and this right here, giving quantity of x minus y dy equal to the quantity of x plus y dx. Rearranging this equation gives quantity of x plus y dx minus quantity of x minus y dy equal to 0. Notice that this equation is similar to the form m of xy dx plus n of xy dy equal to 0, with this as a function of m of xy and this a function of n of xy. Seeing this whole equation, if this is a bit of a second nature to you, we can say that it is a homogeneous ordinary differential equation with a degree of 1. To verify if the equation is really homogeneous, what we do is multiply each variable in the given equation by a variable t. And to say that it is homogeneous, m of xy and n of xy should be functions of the same degree n. In this case, 1. Another thing to remember is that the function should be unchanged even if we multiply it by t. This whole thing right here is shown by this definition. Another way to verify whether the equation is homogeneous is to write the equation as a function of y over x. To do that, we multiply both the numerator and denominator, in this case by 1 over x, so that we can have it as a function of y over x. So there it is. We were able to express it as a function of y over x. It is indeed a homogeneous equation. Now back to our equation. We then proceed to our substitution, which is u equal to y over x. Another way of writing it is y equal to ux. The derivative of y equal to ux is dy equal to u dx plus x du. What we're going to do next is substitute these two to the equation above, so we have quantity of x plus ux dx minus quantity of x minus ux multiplied with the quantity of u dx plus x du equal to 0. We then distribute what needs to be distributed, cancel what needs to be canceled, and now we are left with x dx plus u squared x dx minus x squared du plus ux squared du equal to 0. Factor out the equation again, and since we can still simplify this equation, we divide both the terms by x, resulting to quantity of 1 plus u squared dx minus x multiplied by the quantity of 1 minus u du equal to 0. Notice that this equation is a separable, so we do some manipulations so that we can combine the like terms prior to integration. The right-hand side seems to be complicated. So, we separate this into two terms. Now we can start integrating each term. The integral of dx over x is equal to ln of x. The integral of du over 1 plus u squared is equal to the tangent inverse of u. For the last term, we let some variable v equal to 1 plus u squared. The derivative of v is equal to 2u du. And since we are after of the substitution, we bring 2 below dv. And so we have minus 1/2 times the integral of dv over v. And this is equal to minus 1/2 times the ln of v plus some constant c. But v is equal to 1 plus u squared. So we substitute it back to the equation. So now we have ln of x equal to the tangent inverse of u minus 1/2 multiplied by ln of 1 plus u squared plus constant c. And this is now our solution. Thank you for listening and hope you learned from watching this video.